All right. This is just to tie up some loose ends, okay? We don't have a lot to do today. Shouldn't take more than 10 minutes or 15 at the most. And what I'm going to do here very quickly is give you stuff that you just have to know some terms we've been using these things. We know all we need to know about them, but we're going to actually give you the names of them. For example, we know a lot about the periodic table right now. Think of all the things you can already tell me about it. You can tell me by the group number how many outer shell electrons he has. You can tell me what the last thing you're going to write, S block, P block, D block, F block. All right? You can tell me, you can even predict what charge these guys are going to have, whether they're going to be good metals, non-metals, the size of the atoms. You can predict how hard it's going to be to remove an electron. However, there's a lot of these guys have special names. Even though we've been using them, I didn't actually write it down anywhere. Like yesterday, we went over how some of these guys here, they're in red, they can go both ways. They can go both gain or lose electrons. They have a name. These guys in group 1 have a name. 2 have a name. The only name of a group you know so far is this last group, group A, which is what? I'm sorry, group A, group 8, which is what? Noble gases. The group 8 elements are noble gases. Other than that, you don't really know any of this. So I'm going to write these down, and it won't take me very long. This is not a thinking kind of problem. The ones that you're having trouble with, the ones that I at worksheet in a little bit, you have a lot of trouble with, is where you have to actually think and apply the knowledge, okay? So let's start with the group 1 and group 2 elements. There where you're going to find your best metals. Well, that should not be a surprise to us. The group 1 elements are called the alkali metals, and the group 2 elements are called the alkaline earth metals. They're the best metals. What makes something a metal? Yeah, going to lose electrons. Guys who want to lose electrons are good metals. It's no surprise that the guys in the first group are going to be the best at that because they're the furthest from having an octet. They're the biggest elements in their period. The electrons are furthest away from the nucleus. They're not going to be held as tightly. All right? Okay. So again, this isn't going to take me long. There's not a lot to explain about this. The explanations I've already done. The applications we've been doing, and we're going to do more of it today. This is just some terminology we need to know. And another term of some specific group. By the way, notice I call it miscellaneous groupings. I used to title this for groups. They're not always in groups. Some of them are, like groups 1, 2, and group 7 are called the halogens. But I'm also going to have other elements that have special names because of their grouping, not necessarily in a group. Halogens are guys who are in group 7, and they contain the most active nonmetals. Somebody asked us the other day. I was kind of surprised. I guess I never really actually said it. If a metal wants to lose electrons, what do you think a nonmetal wants to do? Gain it. Yeah. I mean, it's pretty. I thought it was obvious, but whatever. Non-metals, the best non-metals are going to be guys who want to gain electrons. Now think about all the different ways I can ask these kind of questions, right? If I ask for the most active non-metal, the reason, see, you're going to get some of these guys wrong when I'm asking for that in a test question, is that it requires thinking. You know, and it requires, sometimes you have to, it kind of twists your brain around. All right? If I just say who's the biggest or who's the smallest element, that's what you're used to thinking. That's the bare minimum of thinking that you're used to doing. You don't really want to do anything beyond that. So you look over here at this chart, you say, okay, there's potassium, he's bigger than fluorine. I can tell that. That's all. And you think you're doing work. You're not. When I ask who's the most active nonmetal, I have to first ask, what does that mean? A nonmetal wants to gain electrons. Then I have to re-ask, okay, now that I know it means about gaining electrons, who would be the best at it? Well, it'll be guys like in group 7 who are furthest to the right. Guys close to having an octet want to gain electrons. It'd also be the atoms that are smallest. The electrons are closest to the nucleus. Okay? So the group 7 elements, the halogens, are your best nonmetals. All right? No surprise. So here are group 1, alkaline metals, alkaline earth metals, halogens, and we know this group already. What are they called? Noble gases. Okay? Those guys are inert. Yeah.
Hydrogen is a good metal.
Well, now, hydrogen is, there are exceptions to all of these. Hydrogen's a weird guy. He doesn't really fit anywhere. We put him above group 1. He is not one of the alkali metals. Really, he's not considered that. Hydrogen's weird. Because he only has one electron, he doesn't tend to want to lose like other guys do. That's a good point. I never really pointed that out, but hydrogen is a weird guy, and noble gases are weird guys. They don't fit a lot of the trends. Because the trends we've been talking about, who wants to gain or lose electrons? You know, who's a better metal or non-metal? Guess what? These guys, they're neither. Here's a great vocab word, inert. Do you know what it means? You should. It's not just a word from chemistry class. No one's going to ask you on a PSSA English exam what a halogen is. But they will ask you what the word, or expect you to know what the word inert means. It means what? Anybody? Nobody knows. What?
You mean like you can't move or something?
Right, that's a good point, right? And I mean, it's often used like doesn't move around a lot. Basically, it's very inactive. They don't do anything. They just kind of like you guys, just kind of sit around, do nothing. You're inert. Why are noble gases so inert? Why don't they do anything? Who could explain to me why they're not really part of a lot of these trends?
Because they have an octet.
They've already got their octet. They're happy. They don't really want to gain or lose electrons. Okay. So they're very unreactive because they already have a filled outer shell. Okay, and we kind of knew that, but I never, again, all this stuff I'm writing down because I never actually came out and put it in your notes. You will have to know these guys' names. Noble gases, halogens. We're going to talk about, you say, well, just for this chapter? No, forever. Because when I'm talking about halogens and noble gases all the time, you're going to have to know what I'm talking about, which group I'm talking about. Now, the next guys I'm going to talk about are not actually groups. They're groupings of elements, okay? Like, for example, the metalloids. I'm going to go back to my chart here in a second. I always thought the metalloids would be a great name for a hard rock metal band that had hemorrhoids. Right? Metalloids, right? Emily did not like that, but she did give me a hot, and I'll give you that. Thank you. All right, let's go back to my chart here. Take a look.
That's weird.
All right?
Can I have a pencil?
Not right now. Look. Okay, watch. Now, the metalloids, I did, again, this is something, it's another example of something that we've been using, but I haven't actually given you a name for it. This line, which goes like this, down the periodic table, right? You see that line? And he's on this periodic table up there. Did you do backside too? All right. And he's on that periodic table. When I take that stuff down, you'll be able to see it better. It's a red line, and it's a zigzag line. And the guys on the left, I told you yesterday, they want to lose electrons. The guys on the right, they tend to gain. The guys that border it, they're in brown here. Those kind of guys, they're called metalloids because they can either gain electrons or lose electrons depending on who's around them. Okay? All right. So just so you have it written down somewhere, I think we already talked about why that happens. Just quickly, they're called the metalloids. They are the guys that border the zigzag line, and they can either lose or gain electrons. They have more than one oxidation state, more than one charge, more than one common charge. Many guys have more than one charge. All right, well, just have a couple more and I'll be done. Like I said, it wasn't a whole lot to do here today.
Wait, so that like zigzag line that only applies for like the metal or everything. It applies for everything. Like,
I don't know what you're talking about.
Never mind. Okay.
The zigzag line separates the guys who are metals and non-metals. And the ones who border it can do both. It's that
But
simple.
it doesn't separate it from like anything else. Right?
What do you mean from anything else?
Like atomic radius or
No.
no.
It does. It's that direction. It's that way because everything in the periodic table is either largest here or smallest there. But how would you separate it? Like there are only big elements here and only small ones there. I mean, that's obviously that's a relative term. The guy losing and gaining, that's not relative. You're either losing or you're gaining. So the guys on the left lose, the guys on the right gain. That's an either or situation.
For metal.
It's an either or situation for electrons. What they're doing with them. Yes. All right. Let's talk about transition elements. Well, these guys have incomplete D sublevels. Where have we seen them before? We've been doing stuff with these guys for a while. I just haven't called them the transition elements. They're the guys in the middle of the periodic table, right? They're just in the middle. They're the transition elements. They're the ones that have the incomplete D sublevels. And because of that, they can have multiple oxidation states, multiple charges. Reason being, most of the time, by the way, yesterday I told you, I just won't ask you those. All right, yet. I will eventually, but I just won't ask you those yet. All right, because the guys in that D sublevel have electrons that they can lose if they need to make somebody else happy. All right, they can lose them, so they can actually have multiple charges. Some of those guys are +2, +3, +4. They can have +5, +6, +7. Same guy, depending on who he's bound to, depending on his oxidation state. And so, how do you figure it out? Well, you don't. You're not going to have to in most cases. I'm just going to. You'll be able to figure it out either by the way the formula is written or by the fact that I'm going to give you a sheet called the common ion sheet. It's going to have all those common oxidation states for those guys in the middle anyway. All right, so those are the transition elements, the guys in the middle of the periodic table. And finally, you have the rare earth elements. Again, another name you just have to know. You're not going to get this stuff wrong if you study. This is not the kind of stuff that you study for and then you screw it up on the test. No one screws this stuff up. You mess up on things that you have to apply knowledge, and that's what I want to go over next. I want to go over your application of what I've been teaching you for the past week and to specific questions. But let's just, real quickly, the rare earth elements, we don't talk about them a whole lot for two reasons. First of all, they're rare earth elements, but mainly because they're elements we don't use a whole lot. They're a lot of them are radioactive. We don't have, there's not a lot of them around anyway. All right, they're the guys that are in the lanthanide and actinide series, the very, very bottom of the periodic table, kind of separated from the periodic table. And they're the ones that fill up the F, like I told you. But we didn't ask any. I didn't give you any to do as electron configurations. Remember, I told you specifically I wouldn't give you the F guys to do because they are so big. That's the other reason we don't really want to deal with them when writing out the configurations. I mean, we don't really want to write 60, 70, 80 electrons. Who are in there? Well, a lot, like I said, radioactive elements, a lot of the man-made synthetic elements are in there. Most of the synthetic elements are in that series, those two series. They're called the lanthanide and actinide series because that's the first element in that series. If you take a look at it in the periodic table, which I'll show you in a second. All right. Let me show you. Just for the periodic table here. This is the lanthanide series because the first element is lanthanum. This guy here is actinide series is actinium. So these guys are they're kind of cut off on this board here, but they are the bottom ones in the periodic table. We don't work with them a whole lot. You should know what they're called. They're the rare earth elements. Okay. Transition elements, metalloids. Group 7 is the halogens, noble gases, alkaline metals, alkaline earth metals. Okay, group 1, group 2. All right. Now there's a lot we learned about the periodic table. Time to start applying it. Okay, that's what I want to go over with you right now. How we apply this. I'm going to pass out to